Hello everyone. Welcome to the fourth lecture of the sixth module, which is on sequential circuit design. In the last lecture, we were looking at different ways of implementing transmission gate-based edge-triggered resistors. We saw how we can reduce the number of MOSFETs by removing first the inverter from the data path. Then we tried to remove one of the transmission gates from the latches. And then we also tried to go for a pass transistor based design in order to reduce the number of MOSFETs further. In this lecture, we would be looking at another aspect of this sequential circuit design. Another aspect or another way in which we can make these resistors, and that is using the dynamic methodology. Where logic levels are stored in terms of charges on parasitic capacitances available at the internal nodes. And we shall also be discussing about pipelining, which is the most common approach which is nowadays used in order to achieve massive parallelism in your microprocessors or any such design. So the disclaimers remain the same. Let us first talk about the dynamic way of making edge-triggered resistors. So far, we have been talking about the static sequential circuits. We talked about bistable element, which generally use this cross-coupled inverter pair. We saw that we can overpower this cross-coupled inverter pair. We can force it from one stable state to the other stable state by either overpowering the feedback, or we can just cut the feedback using a pass transistor, and then we can connect it when we want it to be hold, right? So that is how we were designing your mux-based, transmission gate systems. However, we saw that, it was a complex design, complex in the sense that, the number of MOSFETs being used was pretty large. And also we require these static sequential circuits only when, we have to hold the state for a long time. If we don't want to, hold the state for a long time, which is the case with the modern data paths or the modern microprocessor, where, the resistors are constantly clocked. So in those cases, we don't need to hold data for a long time. We don't need to hold the system state for a long time in the resistors. And in that case, going for static sequential circuit design would not be much promising, right? We can go ahead with a simple structure, as we saw even in the combinational circuit design, that dynamic combinational circuits were having lesser number of transistors as compared to the static circuit design, static combinational circuits. And we also had, since the number of transistors is less, it would be faster, it would occupy a lesser area. But robustness was something that we were, compromising with. Here also, it's the same case. So if we go for dynamic edge-triggered resistors, we get a simpler structure. And as was the case in dynamic combinational circuit design, here also the data is stored as charge on the parasitic capacitances available on the internal nodes. However, as we also discussed there, the leakage mechanisms or the charge sharing mechanisms may affect the logic levels, and hence it requires periodic refresh. See, here the energy dissipation is mostly going in the periodic refresh process, right? Also, signal integrity is an issue because since the voltage levels or the data is stored as charges on the parasitic capacitance, if there is a cross coupling, if not only cross coupling, if there is this parasitic coupling with some other signal node or with other wires, if there is this problem of crosstalk, then the available charges on that load capacitor that can change, leading to a signal integrity issue. Also, it's not only important to hold the charges at a particular parasitic capacitance, but it's also important to read it. Reading is also a tricky process. Reading an output from this dynamic edge-triggered resistor or any dynamic circuit as such is a tricky process, because when we are reading these circuits, reading simply means extracting some amount of current and generating some voltage. So if you extract some amount of charge, you are basically disturbing the data. So it's like a destructive read process. So in order to read this, what we need essentially is a non-destructive read circuitry, which takes in as small current as possible. That is a read circuitry which is having a very high input impedance that takes a very small amount of current that does not disturb this charge on the parasitic capacitance. So this is another problem, or this is another constraint with these dynamic circuit design. Now, let us talk about dynamic transmission gate based edge-triggered resistors. We ended up with one transmission gate, then a cross-coupled inverter pair, then again one transistor, and then a cross-coupled inverter pair. How we can realize this dynamic edge-triggered resistor? We just remove that feedback inverter from this path. So if we remove that feedback inverter from this path, we only end up having 8 transistors. I'll show you how we end up having 8 transistors. So this is the structure. So there, like the last innovation that we discussed in the previous lecture, it had a feedback inverter like this. If we remove that feedback inverter from the path, we end up having this dynamic transmission gate based edge-triggered resistor. And here's where we have only got 2 transmission gates and 2 inverters, so total of 4 MOSFETs. Further improvement is also possible. I mean, you can realize a dynamic edge-triggered register using only 6 transistors. If you realize this using fast transistor, that circuit also I'll be discussing. And here, how exactly is the data stored? So data is stored on the parasitic as the charges on the parasitic capacitance available at node 1, which is at the input of this inverter and the output of this transmission gate, and node 2, which is at the input of the second inverter and output of the second transmission gate. So what are the different parasitic capacitances that are available or that constitute the C1 or C2? So first we have input gate capacitance of this inverter, which is the gate capacitance of NMOS and PMOSFET. Also we have Cint of these two, NMOSFET and PMOSFET, right? So Cint of this NMOSFET, Cint of this PMOSFET, which includes CGT, I mean the Miller capacitance, I mean Miller coefficient times the CGT. Then it also includes your CDP, CDP and so on. So this capacitance is basically sum of all these capacitances. So now let us see if it is working as a negative latch or a positive latch as we have written it. So when the clock is negative, let's see what happens. When the clock is negative, when clock is 0, then this transmission gate is on and D is sampled to this parasitic node capacitance, which is C1, right? So this transmission gate is transparent when it is 0 and it gets passed to this node. And what happens when this clock is 0 to this portion of the circuit? So when clock is 0, this transmission gate is turned off. So whatever value of QM was sampled here in the previous cycle, that remains here. So this is in hold state. This is in evaluation state or transparent mode. Since it is sampling at negative, when clock is equals to 0, it's a negative latch. Since it's holding when clock is equals to 0, it's a positive latch. Now what happens? If we connect them in this configuration, that is master slave configuration, then what happens? Whatever value of D is sampled at the edge of the clock, rising edge of the clock. So till the clock is 0, D is sampled here. Now this is inverted and QM is basically inverted value of this D. And the moment clock goes to 1, what happens? This transmission gate turns on, this turns off. So whatever value of D was sampled here, it remains there, considering or neglecting the leakages. I mean, some amount of will be lost to leakages, but let us just neglect leakages for the time being. So whatever value of QM, which was D bar here, that gets passed over here and it gets to Q, right? So it's also acting like a positive edge-triggered resistor. We can use it as a positive edge-triggered resistor. Now, as we have done for other dynamic, as we have done it for transmission-based edge-triggered resistor, let us try to find out the setup time and hold time even for this kind of dynamic resistor. So I discussed in the previous discussion session, that discussion was also correct, but now I have understood why exactly this Rabbi or other people, they do not include this inverter in the setup time, and I'll be discussing that. So why they have, so what they are considering when they are calculating setup and hold time or setup and the TCQ, and what we are considering. So let us go ahead and discuss that. So the thing is, what is the meaning of setup time? So the meaning of setup time is that D must be available at QM. This D, how much time before the clock edge should D be available at QM? Or should D be stable? So it should D be available at QM. It's better to write, or it's better to express it as how much time before the clock edge should input be stable, right? If it is stable, then whatever value of D is sampled here, the same will be coming here, right? I mean, the inverted version will come here, but if D is not changing, this value will not change. So one way of looking at it is how much time before the clock edge, the positive clock edge in this case, should our input D be stable? Okay. Now, when the clock is 0, once the input D arrives at this node, if clock goes to 1, then this transmission gate is turned off. So regardless of whether D is stable or not, D is not being sampled at this node. And voltage at this node remains the same. So if somehow you ensure that D is stable till the time its output is its value is sampled at this node, you are sure that the moment clock goes to 1, this D won't be reflected at this node or this node or this node. So you do not need to apply any constraint on stability of D once clock goes to, like, after the correct value of D is sampled here. This is their thought process, right? So ideally what should happen is the value, whatever value you want to sample, it should be available here before, like at the clock edge, it should be available here so that it gets transferred here. But this is special case. I mean, this is not a special case even. So you can understand it from this perspective also, that the moment clock goes to 0, D is sampled over here. And now even if clock goes to 1, then this transmission gate is turned on and nothing is sampled over here. So once this data is sampled here, this QM, I mean, once it is sampled here, after inverter propagation delay, this QM won't change, right? So the thing that I wanted to make clear here is, if D is sampled over here, after the clock goes high, D is not being, like, D is not going to be, like, this node potential is not going to change. And as such, how much time before the clock edge should D be stable? It should be stable only till the time it takes for correct value of D to sample to this C1. Okay. So this is the point that they have considered. So what I'm saying is, what is there, like, they haven't explained it anywhere, but what I could infer was, when after a deep thought I could infer was, arrival of D at node 1 is a sufficient constraint for setup time. Why? Because the definition of setup time is the time period before the clock edge for which the input must remain stable. So if the input D is stable for the time that correct value is sampled at node 1, after that, even if it is not stable, since it is turned off when the clock goes 1, so this value is not reflected here. So this transmission gate delay is sufficient enough to be called as setup time, right? And that is why they call T setup as TP-T1. That is transmission gate 1. However, as we discussed in the previous discussion session, that T setup equals to TP-T1 plus TP-I1. This thing also ensures that there is no setup violation. Actually, this is being on the safer side, because we ensure here that this information of T is available at the input of the second latch. And the moment clock goes too high, the moment clock goes high, this can be, this can be transferred to this queue. But you should understand that setup time is a constraint which is imposed on the inputs. And input is something which is coming from some other part of the circuit. So it is not well within our it is not well within our control. I mean, the level of control that you can have on the inputs is pretty small. Even then, we want to ensure that setup time and hold time constraints are always, followed. But we should try to relax those constraints as much as possible. That is, we do not want these constraints to be very stringent. We do not want, a very heavy kind of constraint on the inputs. So if you are making this setup time as TP-T1 itself, that is also ensuring correct operation, because this, even if the D is changing after that time, it won't affect or hurt your output here. But if you are making this T setup as TP-T1 plus TP-I1, although this is ensuring that, whatever value of D was sampled, it's coming perfectly at QM, but at the same time, you are putting a lot of constraints on the input. You are trying to, hold the, or you're trying to make the input stable for a large amount of time, which is something which may not be feasible always, because these inputs are coming from several different sources, right? Now, if that is the case, I mean, if you have imagined that TSU is equals to TP-T1, then what is your TCQ? The moment this clock goes high, this will first pass through QM, and then it will reach C2, and then it will pass through I3 or I2. It's actually I2. I've written I3 here. So then the TCQ will basically account for the delay of I1 plus T2 plus I3. Now you should understand one thing, that the delay taken, like the delay for this D to go to Q is basically T1 delay plus I1 delay plus this T2 delay plus I3. So the delay remains the same regardless of what you are taking as setup or TCQ. It's just that how you are dividing this so that the correct operation is also, ensured, and you are putting less constraint on your inputs. So let me repeat it again. You can have setup as TPT1 plus TPI1. That will ensure that D reaches this QM, but that is putting over constraints, or to be on a safer side, you are trying to put over constraints on the input. Input is something that cannot be constrained more. I mean, in several situations, you'll find that inputs are coming from some other circuit, so you cannot put severe constraints on them. So even if this data from D, correct data from D, is somehow available or it's sampled at C1 before the clock edge, so you're sure that when the clock goes to 1, this goes off and this data reaches you. Okay, so that was the discussion that I wanted to do. Okay, and what about T hold? So T hold is 0 because the moment clock goes to 1, D is not being sampled here, and as such, when clock goes to 1, there's no need to put any constraint on D, that it should be stable after the clock edge. Okay. So clock overlap is a major concern even for dynamic edge-triggered registers. We saw that it was a major concern for static edge-triggered registers. Here also clock overlap is a major concern. Let's see what happens. So when there's a 0-0 overlap, what happens? When clock is equals to 0 and clock bar is also 0, then both these transmission gates are on. I mean, the P MOSFET of these transmission gates are on. And whatever value of D was there, it can reach Q during that overlap period. And hence, it can create that race condition in which we were supposed to only change the value of Q at the rising edge of the clock, but it may change even at the falling edge of clock if these transmission gates are turned on. That goes against the principle, or that violates the principle of working of a positive edge-triggered register. So for that, what we should ensure is, if the delay that this D has to undergo till the point it gets sampled over C2, if that is larger as compared to the overlap period, this D won't propagate all the way to this node and hence to this one. So if we have this constraint that, if we satisfy this constraint that if the overlap period is smaller as compared to the time it takes for D to get sampled over this capacitance C2, then we'll ensure that D is not propagated all the way to Q. I mean, the value of D, which is incorrectly sampled at C2, it won't propagate to Q. Because eventually, if it reaches C2, it will definitely reach Q, regardless of whatever the clock is. So Q will change anyways, right? So if we ensure even this thing, we are ensuring that this race condition is not happening. What happens in the case of 1-1 overlap? So in case of 1-1 overlap, we can ensure correct operation during 1-1 overlap by just ensuring a constraint on D that it should not change, or the hold condition should be such that D should be held stable for a duration after the clock, which is greater than T overlap of 1-1. Because in 1-1 also, what will happen? This will be 1 if clock bar is 1. This NMOS will be on, and here also this NMOSFET will be on. And D can be erroneously, new value of D can be erroneously sampled to Q, sampled to this node and hence reach Q. So here we have that option. If we just ensure that if we just apply this hold constraint on the input, that this input is held constant after a time period from the clock edge that is greater than the overlap period, 1-1 overlap. So even if D is sampled at this C2, it will be the same value of D since it's falling under that hold constraint. So we won't have any change in Q after the clock edge. So by ensuring a proper hold constraint, we can satisfy this 1-1 overlap. By ensuring this delays, we can assure that this 1-0-0 overlap is also not there, and we don't have this race condition. Now there's a reason why these dynamic latches are not very promising. Although they show you very high speed, less number of transistors, but they're not promising because they're not robust to coupling or noise. Since here you are storing these information in the form of charges on parasitic node capacitances. So if there is a neighboring wire or if there is a neighboring node, because of the parasitic coupling, because of parasitic capacitive coupling, change in the voltage at one of these nodes can lead to a change in the other node as well. Hence, it kind of injects a noise on the other node, and it may even destroy the stored state of the other node. And so we've talked that these dynamic latches are suitable typically when you're clocking the circuits continuously. However, to conserve power in modern microprocessors, you saw that we have this clock gating as well as power gating. So clock is slowed down. So when your battery is low, then even your laptop, it shows that its speed reduces. It's not as fast when it is like it goes to some power conserve mode, and in power conserve mode, your processor speed basically reduces. So clock is slowed down to conserve power when the battery is low. So that is something which is typically done in all the systems right now. So it's not like the clock, like the registers are being clocked as a high frequency always. You can have situations where the registers are not being used at all, using power gating or clock gating. You can have situations when clock has to be slowed down in order to conserve power. So this is also one of the reasons why dynamic logic is not very promising. You need to have something which is, which can even, even if you're not clocking it continuously, it can work fine. And if you're not clocking it continuously, if you're not refreshing it, then leakage currents also may destroy the state. There is also one problem with dynamic circuits. Also, if there is a variation in the supply voltage of some static CMOS circuit within that dynamic latch, then the internal nodes, they do not know about that, because internal nodes are kind of, fed by the input. So the internal nodes do not track variation in supply voltage of inverter. So let's say that, the supply voltage has increased, and as such the VM will increase, right? If the inverter VM has increased, and your internal nodes are working with the previous reduced value of VM, then the noise margins will be reduced. They're not tracking it, basically. So to avoid these problems, what people generally do is they add a weak feedback transistor and make the circuit pseudo-static, which kind of gets back to the previous implementation that we saw in the previous lecture, where we had this small feedback inverter. Why small? Because if it is strong, then it can kind of change the value of D, like it can change the value of D being sampled here, and it can also lead to reverse transmission. So these two were the problems with this. Hence, we wanted to make this inverter strength as small as possible. Okay. Now there is a variant of a dynamic circuit, this dynamic latch, which is insensitive to clock overlap. Let us look at that. That is called clock CMOS resistor or C-square MOS resistor. The structure looks something like this. Here also we have shown a negative latch followed by a positive latch. So this is kind of a positive edge triggered resistor. So you can see that it consists of only 8 MOSFETs, 4 MOSFETs, 4 N MOSFETs, 4 P MOSFETs. And each of these circuits are called tri-state driver. Why tri-state driver? Because depending upon D, this value can either be 0, it can either be 1. I mean, depending upon D and the clock. So let's say, since it's a negative latch, let's say what is the case when clock is 0. When clock is 0, M3 and M4 are turned on. So depending upon D, if D is 0, then this path turns on. It charges X to what? It charges X to 1. If D is 1, then what happens? It discharges X to 0, right? But if clock goes 1, what happens? Whatever value of X was there, it will be retained. Although the leakages will change it, but it will be retained. So it's basically showing high impedance because it's not connected to either VDD or ground in case clock goes to 1. So that is why we call these circuits as tri-state drivers, as the output can go to 0 or 1 or even a high impedance. So let us look at how it is, being used as a resistor. So when clock is 0, what happens? M4 and M3 are on, and whatever is the value of D, its inverted value comes at X, right? This basically acts like an inverter with 2 P MOSFETs in series and 2 N MOSFETs in series. Note that the driving strength of this inverter is weaker as compared to the standard CMOS inverter. So it's in evaluation mode since D is being propagated to X. What about this positive latch? If clock is 0, these two are turned off. So regardless of whatever is the value here, value of Q will not be changed, right? So it's in hold mode. What happens when clock is 1? When clock is 1, this goes to hold mode, and whatever value of X was sampled here, it propagates here, like inverted version of that propagates here. So this is in evaluation mode, this is in hold mode, and as such, at the positive edge of the clock, whatever value of D was sampled here, it goes to Q. Now, I told that it's insensitive to clock overlap, but there's a constraint. It's insensitive to clock overlap only if the rise and fall times are small. If rise and fall times are large, then what happens? For some time, some period of time, all these MOSFETs are conducting, and hence it would be difficult, or it may not be insensitive. It may not be insensitive to clock overlap. Now let us talk about 0-0 overlap. So what happens during 0-0 overlap? So this is the circuit during 0-0 overlap. So when the overlap is like when it's a 0-0 overlap, this is turned on and this is also turned on, right? So M2, M4 is conducting, M6, M8 is conducting. Depending upon the value of D, what may happen, this node X, which is QM, can go from 0 to 1, right? It can only charge. Depending upon if D is 0 or D is 1. If D is 0, if D is 0, if D is 1, nothing happens. If D is 0, this can propagate here, right? This propagates here. And what you have at QM, your QM is 1. If QM is 1 or if this X is 1, M5 is turned on. However, Q doesn't change. Why? Q doesn't change because there's no path, or this is not turned on. Its pull-up path doesn't get turned on. Now, neither its pull-down path is turned on. So in that case, what happens? Whatever is the value of X, it's not reflected at Q. Data at D, although it can, be reflected at X, but it cannot propagate to Q. Why is it happening? Because signal propagates only if pull-up network is followed by pull-down network. Why? If the pull-up network is open, then the output goes to 1. And if this is the input to the next stage, only if the input is 1, only if input to pull-down network is 1, it will get turned on. If you give one input to a pull-up network, it doesn't get turned on. So it kind of exploits the duality of the pull-up network and pull-down network. So a signal from D propagates to Q only if a pull-up network is followed by a pull-down network. Why? Because the pull-up network can only give you output 1, and that output, if fed in the pull-down network only, can change the subsequent stage output. If it is given again to a pull-up network, then it won't change, because one at input of 1 doesn't change the state. It basically turns off the P MOSFETs, right? So this overlap over here is only activating either the pull-up network in both circuits or the pull-down network. So in case of 1-1 overlap, what happens? The pull-down network is kind of, in case of 1-1 overlap, this is also 1. This is also 1. So pull-down network is kind of, activated. Now, depending upon the value of D, what happens? Node X can discharge from 1 to 0. Now, if this is discharged from 1 to 0, this M6 is turned on. And M5 is also, so M6 is turned on, right? And M7 is turned on already. Now, as long as this clock bar is also 1, this is turned off. But the moment clock bar goes to 0, since this is turned on and this is turned on, this can change, right? The value of Q can change. So clock bar going to 0, if the value is changing, that is something we don't want for a positive edge triggered resistor. Clock bar going to 0, we want the value of Q to change when clock bar goes to 0 in a negative edge triggered resistor. But here it's a positive edge triggered resistor, and we don't want the value of Q to change when clock bar goes to 0 and M8 turns on, right? So how can we handle this? So we can handle this by applying a constraint on the input. That is, if T hold is greater than T11 overlap, then definitely this D won't be passed to this Q. This situation won't happen when Q is changing at the negative edge of the clock, right? So by giving this constraint, we can actually reduce, or we can actually even avoid this 1-1 overlap. 0-0 overlap is already avoided, but 1-1 overlap can lead to some problem. It can lead to, change in this value of Q at the negative clock edge, which we don't want. So this can be taken care of by using a constraint on T hold. That is, T hold is greater than T11 overlap. Also, if rise and fall times are, if rise and fall times are not small, if they are large. If rise and fall times are large, then both PMOS and NMOS may conduct, leading to short circuit leakage, and then you may have the problem of this. You may have the problem of short circuit leakage. Some other innovations of dynamic resistors were also, proposed. So you may have thought about this as well, that we are only computing, or we are only letting this resistor work or sample the data at either the positive edge of the clock or the negative edge of the clock. That is, at the rising edge of the clock or the falling edge of the clock. But what if we can make a provision for sampling data at both the edge of the clocks? Then we would definitely, increase the throughput. We would increase the frequency of operation as well, right? So this dual edge register actually facilitates that. So what happens in dual edge register is you can now sample the data at both edges of the clock. So this is the simple circuit of this dual edge register. So it consists of 14 MOSFETs, 7 MOSFETs and 7 PMOSFETs. And as I discussed, the best part about this is that it sample inputs on both clock edges. So here you have 2 master and 2 slave latches, one active at each of the clock edge. And these slave latches are actually complementary. These are the slave latches and they're complementary. So that when one is in the hold state, the other one is kind of in the evaluation mode, and it is transferring that, it is sampling the input at the Q mode. Right? So the advantages, first is there's this area reduction. Area reduces because otherwise you'll have to use 2 edge triggered registers, 2 dynamic edge triggered registers in order to realize this kind of functionality. And also you are utilizing both the clock edges for computation. That is the best part. Now, when the clock is high, let us see what happens. Let us see what happens. When the clock is high, when the clock is 1, then what happens? This D is sampled to X, and this N1 and N2 are basically coming from here. So you are kind of sharing this M2 and M1 to further improve the area efficiency. You are sharing M2 and M1 amongst this master state and this master state to further improve the area efficiency. So if clock is 1, this is on, however this is off. So D is sampled at X, and whatever value of Y was present here, it will remain there. And when clock is 1, this value of Y is actually transmitted to Q, whereas this value of X is held because this is turned off. This is off when clock is equals to 1. Right? So clock is equals to 1. D, this is in evaluation mode, D is transferred to X. This is in hold mode. Whatever value of Y was there, it remains there. This is in hold mode, X is not transferred to Q. This is in evaluation mode, Y is transferred to Q. Right? Now, at the falling edge of clock, when the clock is low, what happens? When the clock is low, this turns on. So X is transmitted at Q. This is off. And whatever value of D was there, this turns on, and that is sampled to Y. Right? So you see at both the edges, value of D is sampled to Q, and as such, you can work with both edges. And as I told, that M1 and M4 are used for recreating master states, so you are further improving your area. Now we discuss about this. Now let us look at a architectural level or a system level trick, which is generally known as pipelining. So what exactly is pipelining? Why is it used? So pipelining is basically, doing these operations or performing computations in your processors or any other such computational unit in an assembly line fashion. So in assembly line, what you do not, process one product at one time. You process parts of any product. For instance, if you're talking about an automobile industry, so a conveyor belt is continuously running. One guy is responsible for, let's say, fixing the seats. One guy is responsible for fixing the steering. One guy is responsible for fixing the engine. One is responsible for, let's say, fixing the body. So the conveyor belt is running. At each step, one guy is doing a particular operation itself. But as the conveyor belt is running, the car is getting made, and out of the conveyor belt, the cars are coming in batches. It's not like all of these will, so it's not like anyone is sitting idle. It's not like the person who has to, fix the body will wait for the person to make the seats or to make the engine. Everything is happening parallelly. Different cars, different portions of the cars are made parallelly. We are not waiting for one car to be made at once and then, work on the different car. So this way, we are utilizing the resources efficiently. And this batch processing or this kind of, assembly line thing is introduced even in these modern processors. You would you would learn about it more in an architecture course. I guess Professor Manak would be taking it next semester, so you'll learn about it more in that. So the reason why we pipeline is to accelerate the operation of data path. Now, before going into data path and so on, let me tell you what exactly any processor in general consists of. So any processor in general, any microprocessor or any other thing, any digital processor as such consists of these several elements, these elements basically. So you have one data path. what exactly happens in the data path? So all the core computations of the microprocessors are performed in the data path, or to say so, all the computations are performed in the data path. It's basically the processing unit of your like microprocessor or the core of your microprocessor. Then what exactly is control? So what exactly it consists of? So your data path consists of several combinational blocks followed by registers to store intermediate values. Because intermediate values are also important. It can be reused and it can make your computations faster. So we have registers for storing these intermediate values. Now what exactly this control module does? It basically tells the microprocessor which action to take at what point of time. That is the role of your control module. So what would be a control module? So control module will be a FSM, finite state machine, which will consist of registers and simple logic blocks. Also, you have this memory module, which acts like a central data storage. Now, this is kind of, the inputs and outputs are interfaced with all these elements. So this is how, in general, any microprocessor architecture would look like. You'll have a data path, you'll have a control module, and you'll also have a memory module. So we already discussed about this data path. We are close to finishing the discussion on the control module, that is the FSM part. In next module, we'll be taking up the memory module. And once we do all this, we would be equipped with enough knowledge to tackle the design of any microprocessor in general. Now the thing is, in general, what happens is, if the combinational blocks are large in your design, then the delay of combinational block dominates, and also till the time the data passes across this combinational block, the other modules will remain idle because this input is not available to the other modules. I mean, the input, which if this combinational block output is going as input to other modules, its output is not available to the other modules and they'll remain idle. And if it is dominating, then the circuit will become very slow. Now, what we do in pipelining is we divide the combinational blocks into several smaller blocks or sub blocks, and then we insert register after each of those sub blocks or each of those modules. Hence, what we are doing by that is we are spreading the computation over multiple cycles in similar to that assembly line function, right? So we are not keeping any module idle at any point of time. We are not waiting for one computation to be done and then going for another computation. We are doing things parallelly. How? We shall see it soon. But the major improvement or the main point why we use pipelining is that it improves resource utilization and also increases the throughput. So let us take the simple case which is given in the Rabaya book, that is, we have to compute log of mod A plus B, where A and B are bit streams. So the general approach is you have A fed to a register, B fed to a register. I mean, at one particular time, A1 and B1 are fed to the register at positive edge of the clock. Next positive edge of the clock, A2 and B2 will be fed. So this register is for that. It is there for sampling the values. So first A and B, A1, B1 are sampled here. Then this is an adder. Adding operation is being performed. Then mod of this is being performed. Then logarithmic log of this is being performed. And then final output is also fed through a register, right? So what is the clock period of this? So the clock period of this, the minimum clock period of this should satisfy setup time of this register plus TCP of this register plus TP logic, right? This should be the clock period of this design. And what is TP logic? TP logic is TP of this adder plus TP of this logarithmic value and plus TP of this absolute value. So this is the case when you are doing it the conventional way. Now, how do you do it in the pipelining way? So in pipeline, what we told was we kind of divide this module combinational block into several sub-modules and then we insert registers in between. So you have this, which remains same. Then you have adder. You divide it into three parts: adder, mod operator, and logarithmic operator, and insert registers between these elements. Now it is the maximum clock period. So it should be greater than TSU plus TCQ plus max of this TP adder, TP logger, or TP logarithm operator, or TP absolute value of this. So if we assume that delay of these three are equal, so basically T clock is greater than or equal to TSU plus TCQ plus T by 3, right? So if TSU and TCQ is not dominating, if it is the combinational logic delay which is dominating, your T clock reduces by a factor of 3 or the frequency increases by a factor of 3 when you go for pipelining. Obviously, you are introducing some more area by introducing these registers, but your clock period goes high. Oh, sorry, your clock period goes low and your frequency goes high, right? So your minimum pipeline time is actually T minimum of this divided by 3. So you're increasing the frequency by 3 times. So what exactly happens in this pipeline? In first cycle, A1 and B1 are sampled and given to the adder. So A1 plus B1 is performed in the first cycle. Now in the second cycle, this A1 and B1 are transferred to this modulo operator and its mod is being performed. However, this module is not idle in that case. The next value of A and B, that is A2 and B2, are also sampled and added in the next clock cycle. Similarly, in the third clock cycle, this shifts here and logarithm of this mod of A1, B1 is performed. However, this modulo operator and this adder operator are not idle. Modulo operator gets A2 plus B2 and new values of A and B are sampled onto this adder and added in the third cycle. So now after 3 cycles, what would happen? You'll get an output every cycle. So first output is coming after 3 cycles. That is the number of combinational blocks, number of different sub blocks. But after first output, in each cycle, you are getting one output. Here you are getting output after 1 cycle itself, but here you are getting output after 3 cycles. So this is the difference, right, between a pipeline structure and a non-pipeline structure. Okay, so now let us do a comparison between the normal circuit and a pipeline circuit. So on the left, you have a normal circuit. You have a register, which is kind of sampling the input. You have a logic block, and then you have a register through which the output is being sampled. So for a normal circuit, what happens? Generally, the result is stored as like the register. So register basically samples that result, or the result is stored in the register at the output. What is the clock period? Clock period is simply this is the minimum clock period. Sorry, So this clock period is kind of greater than TCQ plus TP logic plus T setup. This is what we discussed in the first lecture on sequential circuits. What is T hold? T hold should be less than the contamination delay of the register and the logic blocks. What is the time for this operation? So if one operation is if one such operation is taking T time, this T time, then n such operations will take n times T, right? So time for n operations is n times T. Now here we define another metric which is very commonly used nowadays to classify different processors or different systems, circuits, and that is known as latency. So what is latency? Latency is number of clock cycles it takes for correct input to reach the correct output, or for generating the correct output once correct input has reached it. So for a normal circuit, latency is equals to 1 since everything is being performed in one clock cycle, right? Now let us look at what happens for a pipeline circuit. So for a pipeline circuit, we basically divide this huge logic block into several small logic blocks. Let's say n of those logic blocks, small n of those logic blocks, right? Now what exactly is the time period of each of these individual pipeline blocks? So it's basically it should be greater than equal to TCQ plus T setup plus max of this TP logic time. Let's say if it is divided, this logic function is divided into these blocks having equal delays. So delay of each individual block is delay of this divided by small n, right? So T pipeline is greater than TCQ plus max of this TP logic I, which is TP logic here divided by n plus T setup. So we are kind of increasing the clock speed, right? In the case of pipeline circuit. What about T hold? Now T hold is tricky over here. Why? Because T hold is now less than contamination delay of the register plus minimum of the contamination delay of logic I. Now since we have divided it into several blocks having smaller delay, so even the contamination delay would be smaller, right? So in that case, this constraint is something that we should be very careful about. So we can have a faster clock, but we may have racing condition if T hold condition is not met, and this TCD logic minimum of that is pretty small. So we have to ensure that condition, that race should not happen. Race condition should not happen. Now, what is the time for one operation? Time for one operation is n times t pipeline, right? As we saw in the previous case, first output was available after only n number of cycles or after 3 cycles. So here it will be available only after n number of cycles. But after that, subsequent operations will happen in only one clock cycle, right? So what is the time for n operations, n such operations? It is n plus L minus 1 times t pipeline, which is close to capital N times t pipeline, if n is very large as compared to L. So why this is coming? Because only till latency, only till this latency minus 1, I mean, only till this latency. So first operation is being performed in this number of, like in this number of, like first operation is being performed in n cycles, and latency here is n, right? So it takes n number of cycles for this input to come to output. So latency here is small n. So first output comes after this L, but subsequent outputs come after each of those clock inputs. So if there are n such operations, next n minus 1 operations require only n minus 1 cycles. First output requires L cycles. Next n minus 1 operations require n minus 1 cycles, and hence you have total of n plus L minus 1 cycles, or n plus L minus 1 t pipeline as your time period or the time required for n operations. And typically, if you are performing large number of operations, then this is nearly equals to n times t pipeline. So now time for n operations for simple circuit is n times t. Time for pipeline is n times, n times t pipeline. If your t, if the ratio of this t and t pipeline is kind of, goes as the ratio of the latency, then you are kind of L times faster. Also, with pipelining, one operation is slower because you have added n minus 1 other registers and overhead due to smaller logic blocks. But if you go for large operations, it is significantly faster, as t pipeline is nearly equal to t by L, right? So this is the advantage of having a pipeline structure, pipeline architecture. Now this pipeline is generally used in the data path. So if you have a data path like this, if you have a register file, then a mux, and then a functional unit, and then a mux, typically what is being done is you basically insert new registers over here, and then you divide these operations into several of these sub operations. Those sub operations are operand fetch. So first you fetch operands from first you fetch operands from memory or from some external input, you store in the register. Then what you do, you execute it. This is the combinational block. What you do is you execute it, you perform that particular operation which is intended to be performed, and then you write it back to the memory, or you reuse it in the register. I mean, it depends upon the application, but in general you write it back to a memory location. So just by pipelining this data path, people are able to reduce the clock period or increase the frequency of this significantly. If you want to go into details, so first step is the register will take some data from memory or from some external inputs. So the first process is operand fetch. Once the operands have been fetched, then what happens? We execute it. That is, we perform the logical function, the combinational block function on it, and then we write it back either to the memory location or to the output node. Right? This is how you can pipeline the data path, and you can make use of this pipelining. I mean, you can parallelize these operations and then perform one computation only in one clock cycle and at a faster clock rate, right? So let's say in the first cycle, operand fetch of first operation is being done. In the second cycle, execution of the first operation is being done, while operand fetch of the second operation is being done. Similarly, in the third cycle, what is happening? Write back of the first operation is being done, and execution of the second process is being done, and also operand fetch of the third process is started. So by this, after an end of third cycle, you'll get one output at each clock cycle. So you are performing one operation, one computation at each clock cycle after a delay of these 3 clock cycles, right? This is the advantage of pipelining. And if you want to know more about this pipelining, definitely take the architecture course, computer organization course, or you can also refer to Maurice Mano and Charles Kimes' book. In their chapter 3 and 4, pipelining has been explained in detail. This is not that important for us, so I'm not getting into detail of it because it comes more under the computer organization. So also you can use latches for pipelining. So in circuit design, you can construct these pipeline circuits using simple latches. So here you have these dynamic latches, and you see that you also have these combinational blocks F and G. So the best part about this kind of pipeline based circuits, that first you can use latches. Latches are simpler, flexible, faster as well as compared to resistors. So pipeline circuits are also simple. The second advantage is you can introduce logic also between master and slave. So here we have introduced this F between master stage and the slave stage. And also, as I told already, latch, since it performs better than clock edge register in terms of area and in terms of area as well as speed, and also it gives you more flexibility. So if pipeline circuits can be constructed using simple latches, it's good for us, right? So let us look at this pipeline based circuit and see what's happening over here. So let's talk about the falling clock edge. So at the falling clock edge, what happens? At the falling clock edge, that is when the clock was 1, then in was continuously being sampled here. At the falling clock edge, when clock goes 0, this turns off, and whatever was the value of in immediately before this clock edge is here. Depending upon that, what happens? Input is sampled and F starts computing. So if the input is sampled here, this will go as input to this F, and computations will begin in F. At the falling clock bar edge, what happens? At the falling clock bar edge, what happens? Whatever output of this F is there, it will just get transferred to C2, and then computation of G will start. So falling edge of clock bar means that clock bar was 1, and hence whatever was the output of F, it was sampled at this, and now it has gone to 0, so there's no connection between the two. So whatever output of F was supposed to be there, it is now present at C2, and now computation of G has started. So you see at each of the falling edges, what is happening? The data is kind of propagated along the chain, and we can do parallel things as well. However, here also the constraint is that clock and clock bar must not be overlapping for pipelining, and this has to be ensured at each instance. Also, the pipeline based circuit is race free if you are using C² MOS only if F is non-inverting. If F is inverting, then the signal may race. Why I am saying this? Because if F is non-inverting, I told that clock overlap doesn't lead to a problem only because it is activating only the pull-up circuits or the pull-down network, or pull-up networks of the stages, or the pull-down stage of the stages. However, if you insert in between an inverting element, it will kind of turn on the next level pull-up or the next level pull-down, and hence the inherent advantage that during clock overlap we had either pull-up network or pull-down network as on in both the stages. That is not present when in between stages inverting. So that is why it may lead to signal race, and it should be avoided when using C² MOS latches.